Hello, everyone. My name is Nan Wu from the George Mason University. And today I'm going to present the paper, Hybrid Mobile Vision for Emerging Applications. This is a joint work with the University of Virginia, George Mason University, and the University of Minnesota. Recently, there are many advances in the 3D data capturing techniques. For example, the depth cameras and LiDAR scanners are feasible on the commercial off-the-shelf devices. For example, the newly released iPhone 13 Pro Max is equipped with a LiDAR scanner, so that with this LiDAR scanner, you can scan your room and get a point cloud of your room as shown on the right image here. The CV community has also developed efficient deep learning models for 3D vision tasks. The depth information in volumetric data offers unique opportunities for emerging mobile applications. So in this paper, we start a pilot study that explores the strengths and weaknesses of 2D and 3D vision algorithms. And motivated by our observations, we propose a hybrid mobile vision system that combines the strengths of 2D and 3D vision. We first introduce the system model we propose in our paper. The system model is for the mobile devices equipped with a depth camera or LiDAR scanner. The point clouds will be generated directly from the LiDAR scanner or by combining the RGB and depth streams. So to take advantage of the latency and accuracy trade-off between the 2D and 3D models, our proposed hybrid mobile vision utilizes the output of the 2D vision to reduce the complexity of the 3D vision for tasks such as the object detection and classification or the volumetric content analytics. So here we introduce the motivations of our work. We performed an apple-to-apple comparison between the 2D and 3D models. And we choose the widely used Kitty data to compare the 2D and 3D object detection accuracy. The Kitty dataset offers both the 2D front view camera images and also the volumetric LiDAR point clouds for the same things. For the 2D object detection method, we use the ULOV4 released by its author. And for the 3D object detection, we use the PVR-CNN method released in the OpenPC DET toolbox. The OpenPC DET reports the accuracy of 2D bounding boxes generated by projecting the 3D bounding boxes detected by the PVR-CNN to the front view image, which it can make the comparison between the ULOV4 and PVR-CNN more fair. The table here reports the inference accuracy of the ULOV4 and PVR-CNN for those three objects: the car, pedestrian, and cyclist. And the Kitty dataset classifies the objects using three different difficulty levels. The difficulty level is defined by the matrix of the minimum bounding box height, the maximum occlusion level, and the maximum truncation ratio. As we can see from this table, the PVR-CNN outperforms the ULOV4, especially in the moderate and hard difficulty levels. The only exception is for the easy difficulty level for detecting the pedestrians. The PVR-CNN performs better than ULOV4 mainly due to the fact that it is capable of detecting the occluded objects and also the further away objects, thanks to the depth information in the volumetric data. However, we show here that the inference time for the PVR-CNN is more than 10 times comparing to the ULOV4. Here we show an example of performing the ULOV4 and PVR-CNN for object detection. As we can see from the left images here, the ULOV4 fails to detect the cars occluded by the two cyclists. And also it fails to detect the two further away cars. However, the PVRC then leveraged the depth information in the point cloud, and it could detect the occluded cars here and also the two further away objects. The ULV4 fails to detect this Jeep here, probably due to the fact that there are only a few Jeeps in the training set. So these preliminary results demonstrate that the 3D vision on the volumetric data offers better object detection and classification. However, it is at the cost of higher computation resource utilization. So this observation motivates our proposed hybrid mobile vision. While the 2D and 3D vision combination has been explored recently in the robotics, as well as the autonomous driving, it still remains largely untapped for the mobile applications. So here we propose some research agendas to enhance the mobile vision stack. The agendas can be mainly divided into two categories. One is to enhance the 3D mobile vision with 2D for object detection and classification. Another is to optimize the volumetric content processing with the 2D cues. First, to enhance the 3D mobile vision, we could use the hybrid input data. So this approach feeds the separate input data to the 2D and 3D models. And the underlying idea is to use the 2D vision to handle the easy content and to use the 3D model to tackle the more challenging content. Another dimension of fusing the 2D and 3D vision is to apply different vision tasks to achieve the desired balance between the accuracy and the computation latency. For example, we can use the 2D images for just the simple detection and then use the 3D point cloud for more accurate classification. Or we can use the 2D images for pre-processing so that it can help to reduce the 3D vision workload. Also, the 2D and 3D computer vision tasks can be executed in different locations to balance the key latency and accuracy trade-off. And for the second category, to optimize the volumetric content processing, first, we know that the point clouds can be consumed by training or fine-tuning a 3D vision model for analytics tasks. The training recurs from time to time in order to adjust to the scene changes or the data distribution shifts. And using the whole point cloud for training may incur the computation overhead. So to speed up the content analytics, indexing is very helpful, which the early results that are computed at the low cost on the image can be used to help filter out the point clouds. And the on-device point cloud retrieval is needed when a mobile device wants to localize itself by matching the point clouds for its surroundings with the on-device 3D maps. And the key for matching is to quickly narrow down the candidate 3D maps points. And the system may use the GPS as a geofence. However, the GPS signal is not always available since, for example, the signal could be weak in the urban areas. And also in the video streaming, the 3D data is known to be difficult to compress. So we could use 2D images captured almost at the same time to provide some 2D cues for reducing the 3D data. For example, the compressor could first do a detection, the plane detection, and then later project the plane to the 3D space when for decompressing. So due to the time limitation, I will mainly discuss the hybrid input data scheme and the on-device point cloud retrieval scheme. For the details for other methods can be found in our paper. So here we show how we use the hybrid input data to balance the accuracy and latency on the object detection. We first use a pre-trained ULOV4 2D object detection model to get the bounding boxes of the detected objects. And then we use the 2D bounding boxes to crop out the related point cloud frustum, so that we can not only get the points that belong to the detected objects, but also the points that are occluded by those detected ones. And also we further include the points that are 20 meters away from where the image is taken. The goal here is to include the objects appear to be small in the 2D image. We then construct this new point cloud by combining the points that are mapped to the detected 2D bounding boxes and those remote objects. Finally, we perform the 3D object detection using the pre-trained PVR-CNN model on it. And instead of the original point cloud, this newly constructed point cloud could potentially decrease the inference time due to the reduced number of points. And we report the preliminary experimental result of the inference accuracy in the last row of this table. We use the same KD data set, and overall the accuracy of our proposed hybrid input data scheme is similar to or slightly worse than the PVR-CNN. However, it outperforms the ULOV4 for most of the time. And note that it only takes around 490 milliseconds for our hybrid input data scheme, reducing the inference time by about 20%. The reason is that the PVR-CN's inference time can be reduced when there are fewer points to process. Then to talk about the on-device point cloud retrieval, as I have mentioned, the key for quickly localize a mobile device is to quickly narrow down the searching space, the point cloud searching space. And the 2D images offer rich visual cues, which can be extracted with inexpensive vision primitives. And the resultant 2D features can be used for rough yet valuable estimation. A good example is a previous work called the H-log, which they first perform a global matching with the image retrieval method to get some candidate camera positions. Then they perform the local matching on the points that are close to those candidate camera positions, so that they can do a quick local matching and perform an accurate 6DOF pose. So comparing to this image-based localization, we think that the point cloud-based localization could be more accurate thanks to the depth information in the point cloud. So in our proposed model, when we construct the point clouds for 3D maps, we also sample the 2D features, which will be further aggregated to construct the global descriptors for each individual point clouds. And when to localize, it will collect both the images and the point clouds, using 2D features to narrow down the point clouds for matching. Okay, so to summarize our contribution in this paper, we proposed a hybrid mobile vision system that combines the strengths of 2D and 3D vision for improving the performance of emerging applications such as the augmented reality, mixed reality, and the volumetric content analytics. Our research is motivated by the observations that the latency and accuracy trade-off between the 2D and 3D vision. And we propose some research agendas for hybrid mobile vision that complements the 3D vision tasks, such as the object detection and classification with its 2D counterpart, and optimize the 3D data processing with some 2D cues for reducing the computation and storage overhead. So given the increasing popularity of depth cameras and LiDAR scanners, we hope our proposed research can inspire more work for advancing the mobile vision stack. So that's all for my presentation. Thank you all, and please ask me any questions.